Yeah, can you guys hear me in the back? Yes, thank you. So let's just jump into it. What are actors? Well, imagine you've got a distributed system. It's a little bit hard to see, but these are two nodes. And imagine you've got some kind of resource, like maybe it could be a container, it could be some large shared data structure, it could be a file, in this case it's a file. And maybe you have a couple of threads on node 1 that are trying to access that file. Maybe even have a thread on the other node that's trying to access it. And you have a couple of issues in this situation, right? One is concurrency control. You need to make sure that the threads aren't writing to the file at the same time. You need to make sure there's some kind of way for that thread, thread 3, to be able to actually access the file even though it's on a different node. And you probably want to be able to clean up the file when you're done with it. So actors are just these lightweight processes that solve those three problems. You can think of it that way. So we take the resource in these threads and we put them in these little boxes called actors. And now, instead of those threads writing to the data structure to the file directly, they send a message to the actor who owns the file. This one wants to write, this one wants to read. And now also you can give actor 3 a reference to actor A by just sending it a reference to that actor. And now it's able to also, write to the file, even though it's on a different node. And eventually, some thread on node 1 is going to wake up and it's going to check actor A's mailbox and it's going to process those messages one at a time. So this kind of solves our concurrency and distribution issues. And there's lots of languages that have actors as a built-in abstraction. There's frameworks for every language under the sun, like Java. You've actually got a few ad hoc implementations of actors. If you look at the source code for these frameworks, you'll find that they've invented their own actors. That's kind of fun. Lots of different software that's made with actors. Now, the reason I'm telling you all this is because there's going to be a point in the talk where I'm going to be kind of like when your friend is explaining a really complicated board game to you, and after like an hour you're like, I don't think I really want to play this board game anymore. Just remember this slide when that happens, okay? These are the people we're fighting for. So the situation we're trying to deal with is terminating actors at the right time is really hard. One of the situations we can have here is maybe a task. It's asking its manager if it's allowed to commit, and it's waiting for the manager, but then the manager doesn't reply. And maybe even the TCP connection closes. Now the task is wondering, what do I do? Do we just leave the task running, and then we're underutilizing our cluster, or do we go ahead and kill the task, and then maybe the manager comes back online, it sends a message, and we get some kind of software error. And if you're revisiting these slides later, you can see some real-world examples of this in Hadoop. It's kind of fun to look at. So the problem is basically you have to clean up these actors, you have to kill them, but you don't want to do it too early, you don't want to do it too late, and you somehow have to predict all possible failures that could ever happen, which is, quite a task. So we'd like to have an actor garbage collector that detects when an actor is garbage. It doesn't kill any actors that could potentially receive a message, but at the same time, we want it to kill all the garbage actors. Like if a node crashes and I become garbage, you want to kill me. It was worded weird. And we want it to be simple enough that we can actually prove these two properties actually hold. And generally, we want this to be fast, by which I mean we don't want the actors to block when garbage collection is happening, and we don't want to add too much overhead to those actors either. So this is that slide that I warned you about. Like, we're going to get through this together. The point of this is just to tell you guys that actor garbage is fundamentally different from the garbage that you might be familiar with. So let's look at what that actually looks like. So here we have a busy actor. It's currently executing. And what can the actor do? It can maybe spawn some new actors. It can even spawn them onto remote nodes. You can send messages to an actor. See, when the chicken spawned the two chicks, it gained references to those actors, and now when you have a reference, you can send a message. The messages can also contain references, as I've mentioned, and then actors can also forget references. But notice that these references, they don't really function like channels. That message is still outgoing, even though the chicken doesn't have a reference to the gray bird anymore. So anyway, and now that chicken has finished processing that message and it becomes idle. And when an actor is idle, it means I'm done working, I'm now just going to wait until I receive another message. So if you've been following along, can anybody tell me who is garbage in this scenario? No guesses? Okay, it's the chicken. The chicken is the only one who's garbage, and here's why. So actors are fundamentally reactive, which means that they only process things, they only do computation when they receive a message. So if this chicken is idle right now, it's not doing anything, and it doesn't have any incoming messages, so that is a strong candidate. The other thing that you need to remember is that actors are capability secure, by which I mean that gray bird, it's not going to be able to gain a reference to the chicken because there's just nowhere for it to come from. So we can see now, hopefully, that there's no way for anybody to send a message to the chicken, and therefore the chicken is garbage. I should have really picked better emojis. So that one is garbage, and maybe some computation happens, and now we have the yellow bird and the gray bird, they have references to each other, and they're idle, they're waiting for messages. Who's garbage now? Call it out. Neither of them, actually, because the gray bird, it's about to get a message. When that message is delivered, then it can do some computation. You don't want to kill him. And when he is doing computation, he has a reference to the yellow bird, so he could send it a message. So yellow bird isn't garbage either. So it turns out nobody's garbage in this scenario. But, what if that message got dropped? Now, or what if maybe this node crashed? Interesting question. Well, now look, the yellow bird, it's idle, it's waiting for messages, but nobody could possibly send it a message. So now actually everybody's garbage. So these are the interesting kinds of problems that you have to deal with. In general, I want you to kind of know that actor garbage, the way that we're defining it, it looks generally like those orange nodes. It's just clumps of circles, which is very different from traditional notion of garbage, which is like reachability from a root set. We don't really have a root set. What we're really interested in is, can an actor ever receive a message? So hopefully, if you take away one thing from my talk, it's that. So we have to do a new technique. Oh, and while I'm talking about actors, I might as well mention, I've been talking about detecting crashed nodes, but you might be wondering, how do we actually detect if a node is crashed, right? Because if I send a message to, well, if a node is not responsive, maybe it's just a network partition, maybe it'll come back. Well, in practice, actor frameworks like Apache Pekko and Akka, they have this useful trick, which is if a node is slow for long enough, they just get kicked out from the cluster. And that's really useful from an application point of view, because it means that I can finally, if a node has indeed crashed, I can detect that it's crashed, and I can take some kind of action, and then I don't have to be afraid that actually it was just really slow and it's going to come back, and I'm going to have to face the consequences of my actions. I don't want to face the consequences of my actions. So now getting into the actual garbage collector. There's really two challenges that we want to deal with. One is, of course, consistency. Here's a little example. Here's our chicken and chick again. Imagine that the chicken spawns this gray bird, it sends a reference, and then it becomes idle. And now let's say that we're kind of doing a naive garbage collector. It's just, actors are just going to send information about what they look like right now to the garbage collector, and we're going to see what happens. So the chicken says, well, garbage collector, I'm idle right now, and I have a reference to this yellow bird. That's all the information you know. And now the garbage collector has this view of the world that's starting to build up. Do I need a drink of water? Okay, whatever. I can't even find my water. So now imagine that the yellow bird, what's it going to do? It's currently executing. It might send a message. It might forget that reference, send another message, and go idle. And now it sends a message over to the garbage collector. And it says, I'm idle. I have a reference to the chicken. And now the garbage collector has this view of the world. Some conversation? So the garbage collector thinks, here are two circles that are pointing at each other. If you've learned anything from the past part of the talk, it's that clumps of circles are garbage. So the garbage collector thinks that these guys are garbage, and it's going to try and kill them, which is no good because, as you've learned, oh, thank you so much. I guess I really did need that water. That's really nice. So as you've learned, remember that gray bird, it can receive a message, and it could potentially send a message to the chicken. And the chicken also has this incoming hi message. So none of these actors are garbage really right now. So we really don't want the garbage collector to kill them. So basically we have these two fundamental problems. One is, to get a consistent view of the world from the garbage collector, you need to really carefully time when you send information to the garbage collector. Consistency is really paramount so you don't make mistakes. And the other issue is that we need to make sure that we get enough information from everybody so that we also don't make mistakes. Because if you remember from the previous slide, that garbage collector, it knew about the chicken, it knew about the chick, but it didn't know about the gray bird. And the gray bird, it made all the difference. So here's the key idea. One of the big ideas of this work is that instead of trying to time everything so that we're going to get consistency, we're going to add information to each actor's local state so that if something looks consistent, it turns out it is consistent. So to give you an analogy that I've been advised not to give, but I will give it, imagine like you're taking pictures of an elephant, right? You've got a picture of its legs, you've got a picture of its head, and you're looking at these two photographs and you're trying to decide, do these match up? Are they consistent? Were they taken at the same time? And just by looking at the photographs, you don't know. You have to make sure that the photographs are actually taken at the right time. But what we're doing instead is saying, instead of photographs, what if they were jigsaw pieces? And we have the guarantee that when you put jigsaw pieces together, if they fit, they are consistent. So that's the basic idea, is that we're going from photographs to jigsaw pieces. Or pretend I didn't say anything, if that made you more confused. So what we're doing in that same scenario is we're adding information that we're telling the garbage collector. So the chicken, instead of just saying, I'm idle and I have a reference to the chick, now it's saying, by the way, I also created this new actor. Now the garbage collector has a little bit more information. It knows about that gray bird. And when the chick sends information, it says not only that old information, but it also says, I sent a message and I also sent a reference. And so now the garbage collector merges all that information, and it still sees that the chicken and the chick have references to each other and they're idle, but now it knows that there's this unknown actor that I haven't heard about, and he has a reference to one of my actors. So now the garbage collector says, I'd better not collect this garbage because maybe I don't know what that gray bird is going to do. So that's good. It saved our problem that we had before. And now maybe that gray bird, it actually does get the message and then it immediately throws away the reference. And it tells the garbage collector. Now the garbage collector updates its information and it sees, okay, the chicken and the chick, they're two idle actors. They have reference to each other. They're garbage. Perfect. So we've solved our problem there. Whew. Okay, another drink of water. So I'll take a little cognitive break. Okay. The second, and there's only two challenges, don't worry, this is the second challenge. It's what do we do when nodes crash? So imagine now that our friends are all on different nodes, and we have this situation where the garbage collector knows information from the chicken and the chick, but it's waiting for information from the gray bird. But then, oh no, the node 1 crashes, or it gets kicked out of the cluster for some reason. And now the garbage collector is stuck. Because remember, we added information to each actor's local state so that we would make sure that the garbage collector could find out all the information. And now it'll never get that information that was on node 1. This is really terrible news. Specifically, the information that we wanted to get was, for example, how many messages did node 1 send before it crashed or before it was kicked out? So maybe it sent a message to the chicken, we don't know. Secondly, we'd like to know, well, the gray bird had a reference to the chicken, did it maybe send that reference to any other nodes? So maybe the reference leaked out to all these other nodes in the cluster. And now we're back in that old situation where it turns out we have to scan the entire cluster in order to just figure out, are there any messages left over? Are there any references left over? What do we do? So this is like a fundamental problem, right? How do we recover data that was on a crashed node that we need in order to perform garbage collection? This is the second trick. Instead of asking the crashed node, we just ask its neighbors. Using another annoying analogy, imagine, if you want to get to know a person, you could ask the person what they're like, but you could also just ask their friends and family. Maybe they'll give you actually a more accurate picture of what that person was like. So that's the other big idea. So what we're going to do here is after node 1 crashed, we can't get the information from the gray bird, but what we can do is we can wait for node 2, and we can assume that each of these nodes, as messages are coming into the node, it's keeping track of what messages came in and who they were sent to. So node 2 says, I actually got one message, it was sent to the chicken, tells the garbage collector. Node 3 says, I didn't get anything. And these other two nodes, they say that we got references. So once the garbage collector gets information from all the remaining healthy nodes, it updates its view of the world, and it says, okay, well, actually the chicken doesn't look like it's garbage, because it has this message that's coming in, there's references to it. But look at the yellow bird. It turns out that the only actor that had a reference to the yellow bird has crashed. Its node has crashed. So it turns out that the yellow bird is crashed, and the garbage collector is able to figure that out. It's able to recover after the node crashed or was kicked out of the cluster. So those are the two big ideas. And let's talk about, get away from these birds and get into the machine. This is not a great figure, but it's so cool, and it's in the paper, and I know none of you are going to look at the paper, so I just wanted to show you. I love this figure. The basic idea of how this is going to work is that actors, they send updates to the garbage collector, but they can send updates whenever they want. You can customize this, actually. And the garbage collector, it merges that information from the left, and it builds a picture of the world, like I've talked about before, and that's called the shadow graph. The shadow graph represents its view of the world. And then the garbage collector, at any point in time, while it's merging that data into the shadow graph, it can then trace the shadow graph and figure out from that which of the actors are garbage retroactively. So that's collecting local garbage, and the way that we collect distributed garbage is that each local garbage collector on each node, they're exchanging information about updates that they got from their local actors and messages that they got that have entered the node. They're exchanging that information with each other so that every local garbage collector has an eventually consistent view of the entire cluster. And the remote garbage collectors, in addition to merging everything into their shadow graph, they also build these things called undo logs. And the undo log is basically like a in case of emergency break glass. This is what you do when node X fails. So if node X gets kicked out of the cluster, I'm going to take the undo log for node X, and I'm going to merge it into the shadow graph, and that repairs the shadow graph. And I really regret using the word undo log because it kind of implies that it grows monotonically, but actually it doesn't. It's actually, I expect it to be quite small in practice. We can talk about that a little bit more later. You can get the numbers from the paper. The important part is that I need your help. This was just, this work has been a kind of a proof that we really could do realistic distributed garbage collection in actor systems. But this is just the first step. There's a lot that needs to be done to actually make this really practical, that it make it fit for human consumption. So for example, I haven't tuned really that local garbage collector at all. Things like generational garbage collection, things like how often do actors send messages to the garbage collector. This is unexplored territory, and I think there's interesting points there, basically. And I have a lot more to say about every single one of these things, but I'm running out of time. Another issue is that the actor framework where we implemented this, it's called Apache Pekko, it's a library for Java. And so our garbage collector, it's also a library for Java. And the garbage collector somehow needs to know the references that you're passing around. So right now, we just have to manually tell the garbage collector, I'm sending this reference to this person. So it'd be really great if we had maybe like a static type, some kind of type system, some kind of static analysis that would prevent the user from making mistakes, forgetting to notify the garbage collector about something. I'm about out of time, so talk to me about other things like this. Thank you for listening to my talk, and I would be remiss if I didn't mention I'm on the job market. Thank you.
Thank you very much. Do we have questions? Please state your name.
Hi, this is someone from NYU. Could you go back to slide, I think it was 39. Here, so I'm curious how you get, what happens in a trace where you ask all its neighbors, hey, what did you receive from the pigeon?
Mm-hmm. What's a pigeon?
But say like the chicken haven't received a message. Like the message sent from the pigeon to the chicken hasn't arrived yet, so the chicken says, I didn't receive anything from the pigeon yet.
Oh, and then it arrives after it's reported that information? So the way that that works is when a node gets kicked out of the cluster, you make a promise that you're never going to receive any more messages from that node if they arrive.
Got it.
Yeah.
Okay, thank you.
Hi, thanks for the great talk. Leonard from University of Montreal. I was wondering, it seems like you send a lot of message to the garbage collector. Do you know a bit what the overhead of doing this is?
Yeah, it's really hard to measure. The idea is you can tune it is the thing. Basically, there's kind of a trade-off between how much information each actor stores locally and how often I send messages to the garbage collector. So I give them each a fixed size local memory, and when your memory fills up, you send a message to the garbage collector, and you also send a message to the garbage collector whenever your mailbox becomes empty. But you can kind of customize that sort of thing. Aside from that, there's no messages that we add between the actors. So we actually have an improvement over garbage collectors like the Pony garbage collector, and because we don't have weighted reference counting and our interactions with the garbage collector, there's actually less messages. But yeah, it's really hard to give you a concrete answer on that. It can be tuned, basically.
Hi, Steve Blackburn, Google, at Australian National University. Great talk, I really enjoyed that. What I was trying to do, being a GC person, was map this onto my mental model of how GCs worked, including work I did decades ago on distributed GC, where there's seems to be a lot in common. One thing that struck me is that you said really early on something about Mark Sweep's not applicable because these messages are in flight and blah, blah, blah. It just seems to me that one way to model that is to think of those things as roots. Like so in a normal runtime, you've got all sorts of mysterious stuff happening in the compiler with register spills or whatever else, but we just consider those things to be roots. And as long as the runtime has some mechanism for reporting that to us, then the complexity of that is less relevant, as long as it can guarantee that it can report what those roots are. And I'm just thinking of the actual messages and all the rest of it. If you can model those things as roots with respect to each one of those, that might just be one way to think about it, which takes it closer to classic GC algorithms and so on. And the other thing I was just thinking about is how this maps onto classic distributed GC algorithms. That was more of a comment, maybe a question. I'm not sure, but I enjoyed the talk, and I'm kind of interested in mapping this onto some of the old school GC stuff.
Yeah, that's two great points. The first point is I didn't get a chance to really talk about all the incredible related work that there's been. There's actually been, it's a paper called the pseudo-root approach from Wang and Varela, and they did exactly use kind of this idea of an actor that has messages in its mailbox is a pseudo-root, and we can treat it that way. And that works really well, but their particular garbage collector, it adds a lot of messages, and it doesn't recover from when a node crashes. It can just kind of move on and make some progress while that happens. I've been told that those kind of shared memory tricks add issues with cache coherence. I don't really understand. I'm not like a traditional GC guy, so I would love to talk to experts like you in that space to find out. I also wonder exactly how these things map to one another. I hope that there's some kind of insight that we're not just parroting something that somebody did in 1990. Of course, that's all we're doing, really. But yeah, thank you for your question.
Hello, I'm Kunshan Wang from Australian National University. I'm working on the Ruby programming language, and some programming languages, including Python, Ruby has some notion of coroutines in different form, and Python has generators, and Ruby has fibers. And it's of course it's possible to implement actor model using those fibers and generators, but more often than not, in traditional use cases in those languages, they were used as some kind of iterator or coroutines. The difference between that and actor is that they can't execute autonomously, but they are explicitly suspended or resumed, where there's only one thread of control, swapping between jumping between coroutines. So I think that the idea of determining which nodal actor is live is helpful. And though, of course, in those languages, the fibers and generator also need to be garbage collected. So can some of your thoughts be generalized or specialized, if you prefer, to the coroutines rather than actors?
Yeah, I really should have, in that slide where I had all the actor stuff, there was out over here where you couldn't see, there was all the coroutine stuff that technically kind of counts as an actor. But I'm not really familiar with coroutines, so I don't know how well those processes would map to each other. But maybe if that's like a garbage collection problem, I don't know if the distributed coroutines are a thing that could be.
No, yeah? It is just one machine, one thread.
Yeah. Okay. Maybe there could still be an interesting work there, but I wouldn't know. We could talk about it after.
Thank you.
Thanks so much for your question.
Okay, let's thank the speaker again.